right, so let's start with today's lecture. So today we're going to talk about generating functionals. Specifically, I will consider generating functionals for the connected Green's function, which will be the so-called free energy for 1pi diagrams. With some caveat, this would be the effective action. And for 3 diagrams, to be the classical action. So these will be the subjects of today's lecture. So the first thing is about connected Green's functions. So say generating functional of connected Green's functions. We saw that the full Green's functions, connected or disconnected, were generated by z of j. Right? These were the full Green's function. And we want to see that for the connected Green's function to be minus what we call the free energy. And we will denote by W of j. And we want to prove that the relation between the two is z of j is E minus W of j. All right, first of all, until now, we have talked about Green's functions as things that were independent of j, so we calculated them at j equal to 0. But in principle, we can also calculate Green's functions in the presence of a source j. So Green's functions in the presence of a source j. They're just, again, derivatives of the generating functional, but without putting j equal to 0. So we will denote them by putting a little j index here. So again, these are multiple derivatives of the generating functional. And as a diagrammatic notation, we will denote them like this, with a box with j in it and legs sticking out. So let's consider the one-point function in phi-4 theory. As an example, I mean, the one-point function is, as we'll see, special, but phi-4 theory is just the standard example, being a theory that is scale invariant in 4 dimensions. So then, the one-point function in the presence of j will be obtained just by taking one derivative of the partition function and doing the usual doing the usual calculations, we'll obtain something that is diagrammatically clear. So we'll obtain first a term with a propagator and a source, then a term that involves, so this would be a free term. Remember in the case we put j equal to 0, we would get actually 0 for g of x, but now we're keeping j non-zero. So the first term would be a free term, then we will get an interacting piece where we integrate over interaction point z, and then we have terms like these. So dd, let's say y1, dd y2, dd y3, and then delta of, so one delta is x minus z, x being the index here. Then delta of y1 minus z, delta of y2 minus z, delta of y3 minus z, and then j is corresponding to these y1, y2, y3, right? So notice here in principle we would have had a fourth one, but in principle we would have a fourth one, but when we took the first derivative to obtain g, that got erased. And then we have just gy1, gy2, gy2, jy3. And then more terms like this. So diagrammatically, we would say that this connected one-point function would be what? Well, this term, this is x, and the other notation that we'll use, well, kind of an obvious notation. So this is this, then delta, the propagator, is as usual a line, but also j is now a cross. So this would be, well, let's say quote unquote ij, by which I mean some discrete version of x and y. Then this would be delta ij, jj. In other words, integral delta x minus z, j. So the first term is this, the free one. And then we have interactions. So here we have a 4-point interaction. One propagator takes us to the outside point x. And then these other propagators end in a j. Right? I have from the interaction point to a j. So the next term is this. But I can have all sorts of other terms. I can add things like this, for instance, that's a quantum correction, or even things that are disconnected, right? Lots of terms, all that possible diagrammatics. So this would have loop corrections, and this has loop corrections and is disconnected. Okay, all sorts of such terms. The bottom line is, of course, that by writing this diagrammatically, it becomes very obvious that we can do the same thing as we did for the j equal to 0 case, namely to show that the disconnected diagram is factorized, right? So this disconnected piece, excuse me, doesn't exist in the j equal to 0 case because, you know, the crosses are j's. But in a j equal to 0 case, we considered, I don't know, vacuum bubbles like this, for instance, right? This would be a vacuum bubble for 5-4. So, but the same principle applies. Right? You can draw all possible diagrams, and then in the end, just diagrammatically, it's clear that we can factorize disconnected pieces. So then we say diagrammatically we say that this one-point function in the presence of j is equal to, and here we will denote by this, like meaning only the connecting part, times the vacuum bubble. And you see, the vacuum bubble is something with no external points, but with j's, right? So that would be, so vacuum bubble would be no x's, but j's. In other words, what we would call a 0-point function. Or yet, in other words, 0-point function means non-derivative, so it means z of j itself. Right? So, being that it is a 0-point function, I'll denote it just by a box with a j. Right? Without legs. One caveat though, unlike the case at j equal to 0, this factorization only works for the one-point function. So let's say, unlike j equal to 0 case, factorization only for g of xj. And we can see that because, for instance, for g of x and y, for the two-point function in the presence of a source, we could draw diagrams like this. Right? These diagrams are disconnected but are not of this factorized form. The point is, these are j's, so these do not exist in the j equal to 0 case, but now they exist. So the line coming from an external point can end in a j instead of ending somewhere else. Right? All right. So it doesn't exist for higher point functions, but that doesn't matter. The one-point function is enough. So let's write this diagrammatic equation. Let's write it in formulas. So this is the one-point function, and the one-point function is the first derivative of z, the generating function. So this is dz of j, dj of x. Right? I call this one x. And then on this other side, I have also one-point function. So the first derivative of the generating function of one-point functions. And I define that generating functional to be called minus W of J, right? That's what I said. The generating functional of connected diagrams is called minus W of J. And then I have the 0-point function, which was, as we said, Z of J, right? Okay. And of course, now this is an equation relating Z and W, so just by dividing with Z of J, it's now obvious. So this is d log Z dj, means that log Z of J is minus W of J, plus a constant, because I take derivatives. In other words, that Z of J is equal to a normalization constant, which is the log of this, e to this c, sorry, times e minus W of J, right? And W of J is called the free energy. And remember, Z of J was called the partition function. Now, these names are not random, they're the names from thermodynamics, and you remember we said the partition function wasn't so named because in its correct definition, in Euclidean space with time being periodic with a very large period, then we obtain trace E minus beta H, which is indeed the partition function of thermodynamics. So this is a partition function. And then the relation partition function and free energy is in thermodynamics is this. Okay? So the name is correct. All right, let's move on to the next one, which is more interesting. And as we said, we want to write a generating function for the 1pi green functions, and with a little caveat, this will be the so-called effective action. So what does 1pi stand for? It stands for one particle irreducible. 1pi. Okay. So what does that mean? So it means that if I cut one propagator, I cannot disconnect the diagram. This is 1 degree stronger than connected. Connected means, well, it's connected. But 1pi means even if I cut one propagator, it's still connected. So to see that, well, if I have this would be one particle reducible diagram, because by cutting this propagator, I disconnect the diagram in two pieces. But on the other hand, so this is in phi cubed, right? These are phi cubed vertices. So on the other hand, if in the same theory I write this diagram, this is indeed 1pi, because there's not a single propagator I can cut in here such that I disconnect the diagram into pieces, right? So there's everywhere I cut, there's two. In order to disconnect, everywhere I cut, there's two propagators. Here there's two, well, here there are actually three, and so on. Okay.
What do they move particle?
I'm sorry?
What do they move particle?
Well, propagator is one particle, right? These are two particles. It's one particle here, one particle here. Reducible, reduced to connected diagrams. Yeah, I mean, you could define things with higher. So you could say this is 1 pi, but it's 2 pr, right? And then, well, let me see. Yeah, so this would be in phi 4. In phi. In phi 4, this is 2pi, right? And so you could define this thing. But the only one that's relevant for physics is the 1pi. Well, at least I don't know of any relevant result for the higher ones. Maybe there is. All right, so how do we obtain then the generating functional for 1 pi? And the answer is that we have to take a Legendre transform of the free energy. So going further with our thermodynamic analogy, Z partition function W is free energy. Then when you take a Legendre transform, you can define something like a Gibbs potential, or generalized Gibbs potentials, by taking Legendre transform with respect to one of the variables of the free energy. Right? So one such example is, well, so this in thermodynamics I would call perhaps F, this free energy, that's our standard notation. And then if, for instance, this is an electric potential, this is conjugate, meaning when I multiply with it I get an energy, to electric charge, right? And so the Legendre transform is a Gibbs potential. Right? So that's the kind of thing that that we want to do for the free energy in our quantum field theory. So for us, I mean, this is, if we were talking about spin 1 electromagnetism fields, then this would be exactly what we'd be looking for, because the electric potential is, the electric charge is J0, right? Or charge density, but whatever. Divide by volume. So this would be an exact analog. But now we have scalars, and so our source or current is a scalar as well, J. So that plays the role of Q, right? So we want to find something conjugate. So conjugate to J, like phi is conjugate to Q, right? And the result of this would be the so-called classical field, phi classical of J. And the name classical field, as we'll see, is really well defined. It's really, in a quantum theory by the Ehrenfest theorem, what becomes the classical object is the VEV of the quantum operator. right? So then we define this phi classical is just the normalized Z in the presence of J, right? So this is the one-point function. And this is the 0-point function, right? So you can write it as 1 over z, the 0-point function, and then write explicitly the path integral in here, minus s of phi plus j phi of x. But also we remember that this is the derivative, the one-point function is the derivative of z with respect to j of x. So 1 over z of j, d z of j, dj of x. But this is just the derivative of log z with respect to j. This is just minus the derivative of w, right? So then, indeed, this is the connected one-point function. Right? We've defined minus w. When writing this here, we've defined minus w as the generating functional of connected diagrams. All right. And to get a better understanding, let's consider the example of a free theory. And moreover, dealing with continuum objects is a little bit cumbersome. It's better to deal with discretized version. It becomes easier to understand the diagrams. So I'm also deal with the discretized version. So then S, the action is just an S0. So minus j phi, that would mean d phi squared plus n squared phi squared, and then minus integral j of x phi of x. But we want to, and this would be understood as phi delta phi, phi delta minus 1, inverse property of phi. So this would be integral, understood as integral ddx dy, phi of x delta minus 1 x and y, phi of y, minus integral ddx j of x phi of x, right? But as I said, we want to discretize to understand better to make it easier to understand diagrams. And so I would write a discretized version, which is this one, right? So then the classical equations of motion So this is the action in the presence of a source, right? The Euclidean version of the action in the presence of a source J. So the classical equations of motion are given by putting the variation of the action in the presence of J with respect to phi to 0. And I want to think of this as a discretized version. So ds of ji respect to d phi I of j is equal to 0. So varying here, we get two terms, cancels the 1/2, delta minus 1 ij phi j minus ji equal to 0, or phi I is delta ij phi j, right? That's why I put these things discrete. It looks somewhat easier to picture, but we could do this also in a continuum, and this classical solution would be just the solution of using a Green's function, the solution for a potential using a Green's function, right? So integral d dy delta x and y j of y, right? Think of this as a Coulomb potential written in terms of the Green's function and the source. Okay? On the other hand, this is a quadratic action, so that means that z is the free partition function, which is e to 1/2 j delta j. That is ji delta ij jj, right? Which means that the free energy, so this is also equal to E minus W of J. The free energy, W0 of J, is equal to minus 1/2 Ji delta J Jj, right? So in this case, the classical field, as we saw, is the differentiation of minus W. So phi I classical, but also in this free theory, so I put a 0 here. This is d minus W with respect to ji. I use discrete notation. So minus W, so I can write it like this, minus W is 1/2 J delta J. So with respect, differentiating with respect to J, I get two terms, cancels the 1, so this is delta J Jj. So it's the same result as the classical result. So same as the classical solution. Okay, and that's not surprising. The point is that free solutions means they are really classical. Only tree diagrams. I mean, not even tree, but tree diagrams without interactions. No interactions. in particular no loops. So this is really the definition of a classical theory. No loops, no quantum interactions. Right. And as we said, we define this was the connected one-point function, as we saw here. This was, well, I wrote it somewhere, but it was the connected one-point function. And we already denoted that like this. So the full one-point function was denoted like this, right? And the connected one-point function, which now we call phi classical, is denoted by a circle with J and a line sticking out of it. All right. All right, so now we're interested in this 1pi range function. And let's consider, as before, phi-4 theory, just it's easier. And let's see how we draw some diagrams then for this classical field. Okay, so this would be the classical field, and so what can happen? Well, it can happen that I end in a J, so that before, but the only difference is that now this is connected, so I can forget about disconnected pieces. So I can have this, then the next term that we wrote already diagrammatically is this one, where I have an interaction vertex, but then out of it, all of the remaining lines also go to J's. Then I can take this line and draw a line like this. So this has one vertex, this has two vertices. Other things I can do, for instance, things like this. This has many vertices, 3, 5. There are many things I can do, right? But now, what I want to do is to think diagrammatically of how I can write this in terms of 1pi diagrams. So first of all, I will, when I draw a blob like this with crossed lines, I mean this is 1pi. So I can put legs on it or something. But I want to differentiate. So for full function, I have this box with a J in it. For a connected piece, I have the circle with a J in it. But now I write a shaded blob for 1pi. So then So then I want to understand how to write this in terms of 1PI diagrams. Now, the first possibility is, well, it is what it is, it's the free one, right? But then, I guess I should have. I'm sorry?
So replacing the box with the leg with a block.
Right. Yeah, I was just trying to give an example here to add some more diagrams in here. Well, I don't know if perhaps there is no such thing in 5.4. Let me think. I try to write this 1PI. Yeah, I cannot think of a diagram right now, sorry. But anyway, in principle, the one thing that could appear next after this, instead of ending in a j, I could end in a 1PI 1-point function. So I could, so I should have said I don't put, in here I put propagator sticking out, a leg sticking out, right? But that's fine because these are disconnected and connected. But if I have 1PI, I cannot put this because I cut this propagator, I disconnect the thing. So that's why the 1-point function is this, and then the 2-point function is this, and so on, right? Since because I put the leg, then I can cut it. So the next possibility then is I can have this, right? Then I could have the 2-point function in here, the 2-point 1PI. But then I have this extra leg, and what could I do with it? Well, I could do anything, since this is already the 1PI part. Here I can only have a leg sticking out, because the 1PI part is already taken care of. So the only thing I can have is something like this. So this is a connected diagram, so it has to be of this type. So any other connected 1-point function sticking out there, it would be okay, right? Okay. Then what? Well, I can have, so, yeah, this is still not part of what I drew. Anyway. So, the next possibility is to have the 3-point function. And again, since this is 1PI, everything coming out is 1P reducible. So I start with a propagator, and then I can have anything. So then I can have J, right? And so on. Then the 4.1 pi, again ending in logs. And this is the the only one that I drew here, which is, oh no, sorry, I drew also this. This is a diagram from this, right? This is a diagram from this, where in here I just end on a J. And then this is a diagram from this, right? Where I have a 1 pi part, and then things sticking, and again, these things just end on a J. All right. There's one more trick that there's a permutation of these external lines. So on the permutation, they give the same thing. So I have to divide by the permutation, number of permutations, 1 over 2 factorial here, 1 over 3 factorial here, and so on.
I don't see where the second diagram fits the one which has only one vertex.
Yeah, sorry, this is also part of this. Right?
Okay.
The 1 pi 4-point function starts with just a 4-point vertex, right? The other ones no, because there are no 3-point vertex, but this one starts with a 4-point vertex. Okay, so now let's write this diagrammatic equation as a algebraic one. So the 1-point connected 1-point function is phi classical. And then this is a propagator. So I start all of them by a propagator. Right? Then in the first one I end just on a J. But in the second in the second one, yeah, I forgot why is there a minus. Yeah, I suppose it's just a definition. So this one I will call gamma, but it's a 1-point function, so it has an index I, or rather if this is I, this is J. Right? So gamma J. Then the 2-point function, 2.1 pi function I will call pi, that's the only one exception, no Cy. Right, so this second one is plus pi jk, and then this thing is just the original phi classical, this block. Right? This is phi classical k. Then I have 1 over 2 factorial. Here I have the 3-point function, which I will call again gamma jkl, and again the things that I attach to them are phi classical plus 1 over 3 factorial gamma jklm. Yeah, I mean, okay, let me write the general term. So 1 over factorial gamma j I1 In phi I1 classical until phi In classical. Okay. So we've called all the 1pi functions, we call them gamma except for the 2-point function that we called it pi. So now we see that we can define gamma hat of phi classical as well, basically this thing multiplying phi except with a different coefficient divided by n. So n plus 1, sorry. So phi gamma I phi I plus pi ij phi j phi k 1 over 2 factorial plus 1 over 3 factorial gamma ijk phi I phi j phi k, and then perhaps also write the general term 1 over, let me write it like this, n plus 1 factorial gamma I1 in phi I classical phi I1 classical phi In classical. Right? So then you see that by taking derivatives with respect to phi, derivatives of this, I get all these terms. Right? That's how I wrote this function, which means this is a generating functional for the 1pi endpoint functions. Right? In other words, the statement is that I take this gamma n and I obtain it from the nth derivative the dji1 djin of this gamma hat phi classical. Sorry, phi. Okay, at phi equal to 0. And in particular, the one that we're interested in here is, so the term that we obtain here is the 1 point function, but in the presence of phi. So, so the equation, perhaps, let me write it in here. This equation becomes what? Becomes phi I classical, which by definition was the derivative of minus w with respect to j. And this is what? This is delta ij, and then ji. And here, as we said, this is the full 1 point function for non-zero phi. If I don't put phi n equal to 0, then for the 1 point function I get all of this, right? So 1 point function, that is to say the gamma hat of phi classical, the phi, sorry, this is jj, phi j classical. Okay? So my self-consistency equation, which I derived diagrammatically, reduces to this. And now let me multiply by delta minus 1 from the left, and then take this term to the right, d gamma. So d gamma hat d phi I classical plus, or minus rather, minus delta minus 1 ij dw dj no, sorry, I don't want this. I just want to put the phi classical. So I just leave it like this, phi classical, equal to, and now delta has disappeared by multiplying with delta minus 1, so I'm left with ji. Okay? So, I can write this as derivative with respect to phi of some modified function, d phi I classical, and then here I have gamma hat of phi classical, but then I have this extra term which comes from a 1/2 phi I classical delta minus 1 ij classical. Okay? And so we define this function as the effective action. And we called it gamma without the hat by classical. Gamma hat by classical plus 1/2 by classical delta minus 1 ij by classical. So this is what I call the effective action. And if I define this, then at the full quantum level, I have that by differentiating this effective action with respect to phi, with the phi classical, I get ji, right? So this is the quantum version of the classical equation of motion. As I said, by the Ehrenfest theorem, phi classical is supposed to be what replaces phi in the classical theory. And then through this derivation, which I did, I showed that gamma is the effective action is what replaces the action, because the classical equation would be just variation of the action with respect to phi equal to ji. Right? So at the quantum level, I replace the action with the effective action. All right. And then for this effective action, I can define these endpoint functions as well. So I define it just as in the case of gamma hat. Right? Just like in the case of gamma hat. The only difference again is in the 2-point function. So now we see why I define in gamma hat I defined pi ij, the 2-point function as pi ij, and the other ones I call them gamma I, because by defining it this way in the effective action, really, looking at this relation, the only difference is in the two-point function, the term quadratic in the phi's, right? So from this, first of all, I would say gamma I1, In is dn d phi I1, d phi In, gamma phi classical, and phi classical equal to 0, right? The same one as for gamma hat. And then we see that so yeah, here I should say, I should have written except for pi ij. So gamma I1 to In except for pi ij. Pi ij then is the two-point function. And here, however, I define all of them like this. And then the only difference is in this two-point function, that gamma ij is pi ij to the two-point function gamma hat plus this inverse propagator, right? Because in here I already have the 1/2 factorial phi j, and the rest is gamma hat, is delta minus 1. All right. So that means that in the effective action, all of the terms except for the two-point function are diagrammatic and 1 pi. So let's say in gamma, all gamma I1, In are 1 pi and diagrammatic, except for gamma ij. Gamma ij contains the diagrammatic and 1 pi part, and then contains this inverse propagator, which is neither. It's not neither diagrammatic nor 1 pi. I mean, this, so it's nothing. Okay? All right. So gamma hat is the generator of the 1 pi function, but the effective action is gamma hat except for the two-point function. All right. Then finally, I come to the question that I started the discussion with. I said that in order to obtain the generating functional of 1 pi, I have to do a Legendre transform on the variable, so I go in the free energy, so I go from J to phi classical. All right, so let's see that. So let's write this as a theorem. Gamma effective action, phi classical, is the Legendre transform of W of J to free energy. So what we want to show, let's put this in exponents, so E minus W of J, I want to, E minus W of J, which is the partition function, and therefore is integral d phi E minus S of phi plus J I phi I. If this is the Legendre transform, I also want to write this as E minus, and then the Legendre transform would mean gamma of phi classical, and then plus Ji phi I classical. So let's see that. So another way would be to say, so then we'd have the gamma of phi classical is W of J plus J I phi I classical. And we'll just take derivatives of this. So d phi in this relation. Then we get that the left hand side, taking derivatives, here we get d gamma phi classical, d phi I classical. Right? But remember what we've proven before. This is just the quantum equation of motion, so this is equal to Ji. Right? But on the other hand, if this is true, I would have the derivative of W with respect to phi classical, except that W depends on J. So I would have to differentiate first with respect to J K, and then by the chain rule derivative of JK with respect to phi classical. Okay. And then derivatives in here. So one term is differentiating J also. So let's say d, yeah, perhaps let's call this K. So d jk d phi I classical, then phi k classical, and finally differentiating phi itself, I get the Ji. Okay, so the Ji term is there. So the only question is about these two terms, right? But then I remember the definition of phi classical. Remember that phi classical I is the one point connected Green's function. And minus W is its generator, so this means this was minus W dW of J dJi, right? So I write this as equal to minus phi k classical, and then I just cancel these terms. Okay. So I have minus phi k classical, the same, times dj k d phi. Okay. So that means that this equation is consistent with differentiating with respect to its value. So then it can, the two are equal up to a constant, which is, as always, irrelevant. You can always drop a constant from these functions. Okay? So we've proven this. All right. So the effective action is the generating functional of 1 pi, except for the 2-point function. But that doesn't sound so impressive. I mean, what's the big deal about all of this? Well, the big deal is that, as we saw, the quantum equation is is the equation of motion of the effective action, which means that the effective action contains all the information about the quantum theory. In the same way, or the observable information, say, about the quantum theory, in the same way as the classical action contains all of the information about the classical theory. Right? So, solving the theory is equivalent to finding the full effective action. Solving quantum theory is equivalent to finding the full effective action. So, as an example of that, I mean, obviously, the examples where you can actually do a quantum calculation and find the whole thing, explicit quantum calculation and find the whole thing, are very few and far between. But there are cases where you can make use of various properties, symmetries, and various other holography and all sorts of holomorphicity and all other sorts of things. And one rather famous example where an effective action was found is the theory found by Seiberg and Witten. In that case, however, they only found the low energy effective action. So the full quantum effective action, but at low energies. That's why this paper is so famous, because it's basically solving the low energy quantum theory of a quantum field theory. I mean, supersymmetric and it doesn't look very much like CCD, but it looks enough. So people got very excited when that happened. All right. Also, another important object is the connected two-point function or propagator. Also a very important quantity. So we saw that the connected one-point function found by differentiating the generating function of minus w with respect to j. This was called the classical field. But then the two-point function, connected two-point function, is taking one more derivative, right? So this is the same as taking the derivative of phi classical with respect to j. But then we had, I erased it, no? But well, let me copy it again. We had this long formula for the phi classical. This is delta ij, jj minus gamma j plus ijk phi classical. Plus 1/2 gamma jkl ik classical plus dot dot dot. right? So taking derivatives now with respect to j, this is d phi classical d j, right? I get delta ij from the first term, and then this one is independent of j, so this goes away. Yeah. And then this one, so these endpoint functions are independent of j, they are functions of phi in principle. They're functions of phi. Well, this one, okay, so there's an issue about this one, let me think about it, but first let me say what the issue is. So I want to write, so in the end I want to consider the connected two-point function independent of j, so at j equal to 0. Okay, so I want to drop terms that depend on j. But for physical reasons, I assume, remember that the classical equation was that phi I was delta ij phi j, classically, right? Sorry, phi jj. So I also want that correspondingly to this classical equation, also the classical field when j equal to 0 also goes to 0, right? In the same way as the original field in the classical equation of motion. So that means that when I put j equal to 0, I will drop terms with phi's, with remaining phi's. So I'll write only terms that do not have phi. So when I differentiate with respect to j, this doesn't have phi's. And then there's this term which I'm a little bit confused about. In principle, this depends on phi. Oh well. And here, in all of these later terms, if I would differentiate pi jk, so pi depends on phi, and phi itself depends on j. So if I would differentiate these phi's and gammas, I would still be left with something, some phi multiplying it, but phi goes to 0 when j goes to 0. So I don't care about these terms. So the only term that I care about is pi, delta ij pi jk, right? And then differentiating phi k classical with respect to ji, I get the same two-point function. So g ki connected, right? And then I say plus order j, by which I mean, as I said, terms that vanish when j goes to 0. So when j goes to 0, then I can write exactly pi jk j k. Oh no, I'm sorry. I scrubbed the indices, no? Didn't I? Yeah. So I differentiate this phi I with respect to jj, and then all the other indices are dummy. So k, kl, and then phi l with respect to jj, right? So this is j, lj. Okay, so once again, ik, kl, kj. Okay? All right. So now, now I rewrite this. This is a self-consistent equation for GC, but I can move the term of GC on the other side and give a common factor GC. So I get delta ik plus delta pi. Within this is ik, so pi l lk. Then g kj connected equal to delta ij. Right? And now I can multiply by delta minus 1. And get here then delta minus 1 ik plus pi ik jkj connected is delta ij. And so finally, then I also remember that this is called, so this pi was the term in gamma hat, which was the 1pi 2-point function. But by adding delta minus 1, I get the term in gamma, which is the effective action. Right? So finally I have gamma ik gkj connected ij. Right? So the connected 2-point function is the inverse of the 2-point effective action. Okay. I can also write this explicitly, so I can say I can write this as 1 plus delta pi as it matrices GC equal to delta, and then GC equal to I have to multiply by 1 plus delta pi inverse on the left. So 1 plus delta pi inverse delta. And 1 over 1 plus x is 1 minus x plus x squared minus x cubed and so on. Right? That applies also for matrices. And so I write this as 1 minus delta pi plus delta pi, then minus delta pi, plus and so on. Delta is delta minus delta pi delta plus delta pi delta minus and so on. Right? If I want, I can also put some indices on it to make it more explicit. So let's say GCIJ is delta Ij minus delta Ik IKL delta Lj plus delta Ik IKL delta Lm delta pi mn delta nj, so on. And I can also write this in terms of diagrams. This is the connected two-point function. And then this is a propagator, then minus propagator, then this pi is the 1 pi, delta is propagator again, plus propagator 1 pi, propagator 1 pi, propagator, minus delta. So all of these things, right? And you see that this equation is actually diagrammatically obvious. Only the signs are perhaps not obvious, though if you think about it this way, you come to them. But otherwise, it's kind of clear what can happen. So you say, what can happen when you start here, we go towards the right? Well, you can either have a propagator, a free propagator, or a propagator, and then a bunch of 1 pi stuff, and then one more propagator, or so on. All of these possible terms, right? All right. And the other point is that I wrote the relation like this, right? So I can say, another way of saying it is that GC is gamma minus 1, GCIJ, gamma minus 1 ij, right? That's another way of saying it, right? And you note now, remember this is in the effective action. Gamma, the coefficients gamma are the coefficients of the effective action. So this is as saying that if I have in the action a term phi I delta minus 1 ij, this let me call it kinetic operator, kij phi j, then the propagator delta ij is equal to k minus 1 ij, right? And now I say at the quantum level this becomes the effective action gamma. So this starts with this term, right? And what I'm saying now, so the equivalent statement is that this GC ij, that I can also call the quantum propagator, right? Which starts indeed with a classical propagator delta ij, is equal to gamma minus 1 ij, the inverse of this kinetic propagator, kinetic operator in the effective action, right? Okay. Now the final issue to be tackled is the generating functional of three diagrams, and see that that is the classical action. So let's say classical action as a generating functional of tree diagrams. Now when h bar goes to 0, the effective action should become the classical action. So another way of saying it, that the effective action is just the classical action plus quantum corrections. Right? But in this case, the 1 pi corrections vanish. Because 1 pi means things like that. We have at least 2 lines that we need to cut, and that amounts to loops, or in other words, quantum corrections. And we are left with just vertices. Just plain vertices. Okay? But then, well, what happens in this case to the diagrams? Well, diagrams then becomes just tree diagrams. Right? They just have propagators and vertices, but no 1 pi parts, no quantum corrections. So they can only branch out like this. Okay. Now, the thing is, when I consider tree diagrams, these are still Feynman diagrams. So I still have quantum mechanics. Right? Quantum mechanics means from the tree diagram I calculate an amplitude, and from the amplitude I calculate a probability that is the modulus square of the amplitude. Right? Amplitude or wave function, if you want to think of it this way. So we still have quantum mechanics giving us probabilities for events. So you will hear a lot of people saying, and people get confused about this, even senior people sometimes, tree diagrams are not classical theory. Tree diagrams are classical field theory, but quantum mechanics. Let's say it here. Okay, quantum mechanics in the sense that what we're calculating is amplitudes for stuff to happen. In particular, it's clear that if I consider, say, I don't know, yeah, just a decay of something into 2 particles, right? Then, of course, you all know radioactive decay is a quantum process that happens with probabilities. Right? There's nothing classical about it. And you could have said, well, this involves just 3 microscopic particles, so clearly it's a quantum process. Right? This is quantum mechanics. What it is not is quantum field theory, it's just classical field theory. Okay?
Why? I don't understand how.
All right. So what is quantum mechanics? Define for me quantum mechanics. How do you define quantum mechanics? Just say in your own words.
We don't have a deterministic word anymore, and
And we have probabilities for things to happen. Right?
Amplitudes, you calculate the amplitudes and then experiment to get probabilities. Just
So
that's
we have quantum mechanics. We agree on that then?
yeah.
Okay.
But
On the other hand, I've taken h bar to 0 in the effective action. That is, I have no quantum corrections anymore. Right? I only have the classical action. I don't have the quantum action. Right? So this is classical field theory, right?
I have a question. Is it somehow related to first quantization and second quantization?
Yeah, I was about to say that. So first of all, well, I don't particularly like that name because it's misleading. The way to think about it is in this way. But if you want to, quantum field theory is called sometimes second quantization. It's a rather misleading fact, as I said in the first lecture. The idea behind this is that you take a wave function, which is in quantum mechanics just a function, and you make out of it an operator. So you quantize it, quantize the wave function, right? But it's very misleading because it's not another quantum mechanics on top of the regular quantum mechanics. Moreover, thinking about the field as a wave function is wrong. It's correct in some specific cases, but in general, it's wrong. So yes, if you want a mnemonic, you can think of it, what we have is first quantization, but not second quantization. But only as a mnemonic, you don't, strictly speaking, this is wrong.
So this what we are saying is the same thing as, for example, quantum field theory work with the saddle point of the action. The saddle point. If I were to
Right, there's another way of saying it. And also, you have to.
quantum field theory just with the major contribution.
So, first of all, you also have to understand the classical limit of a field. So as I also mentioned this fact when talking about fermions, I said that strictly speaking, fermions don't have a classical field theory because there's no notion of a classical field for fermions, as fermions have only one particle in one state. The classical limit of a field means that there are many particles in the same state. You have the standard example is the two-slit experiment, which now it's a standard tabletop experiment, and you can do in undergrad, where the double slit, you make a wave hits it, but nevertheless you see on the screen, the screen that is transformed into for you to see, you see photons individually hitting it, right? So that's clearly quantum mechanics. But then if you have many photons, if you accumulate many photons, then you start to see the interference pattern, which is a characteristic of the classical wave of electromagnetism, right? So when you have many particles, the field becomes classical. It behaves as classical. You might have quantum corrections, but if you don't care about quantum corrections, then it's classical, right? But the point is, in here, out of this field, we're still constructing just probabilities for single particles. So we're still doing quantum mechanics. Okay? To be a purely classical theory, I would have needed to consider many particles. And that's not what I'm doing. Okay? All right, this is an important point, and I've seen many important physicists getting confused about this. So it's good to understand it. There's another way of putting it also. So when we're doing these three diagrams often have quantum corrections. But as you might know, and as I will show explicitly later on, many of the early successes of QED were just from three diagrams. We're just calculating some tree diagram in QED and therefore calculating some amplitude and some probability for some effect. Right? And that was still called QED, it was not called classical. Right? All right. Good. But now, if we're interested in the action is just a classical action. So we have classical action. And for example, I'll take the phi-4 theory as an example. We have the standard kinetic term and interaction. And then, as we know, the equation of motion in the presence of the field would be this is equal to Ji, in the absence would be equal to 0. So we get delta minus 1 ij, phi j, plus lambda 3 factorial phi I cubed equal to Ji, right? That would be my classical equation, which is valid in this tree limit. And then the classical solution is obtained by multiplying with delta, from the left. So it's delta, and putting this term to the right. So it's delta ijjj, right? And then minus lambda over 3 factorial delta ij phi j cubed. Right? Of course, this is not a true solution, it's a self-consistent equation, right? Because phi I appears on both sides of the equation. But if lambda is small, that is to say in perturbation theory, very important to realize this is now classical perturbation theory, right? I can solve this self-consistently, right? Just a moment, let me make sure. Derivative diagrams. Yeah, okay. Yeah, so I'll tell you just the first iteration, because the second iteration I left as an exercise. But anyway, it's clear how do I solve this self-consistently, right? You know how to solve a self-consistent equation in perturbation theory. You just, so if the right-hand side, term on the right-hand side is small, you take the field as just the zeroth order term and you put it back on the right-hand side, right? So, yeah, first of all, let's write this diagrammatically. So this would be my field phi I, and I would write it as propagator ending in a source, and then minus propagator, and then I have a vertex, out of which I have 3 remaining, or in general, n minus 1 remaining phi fields. So here this, right? So this is my self-consistent equation. But now in the right-hand side, I substitute this with just the first term, right? So I write this minus but then I'll not tell you the next term because that's part of the exercise. But I hope you have grasped how to do it. Let me see, was that all? Yeah, that was. Yeah, so the point is by doing this, all of these iterations, I will get, as you can easily see here, only 3 diagrams. And moreover, all the 3 diagrams. Okay, so this is what we meant by saying that. Well, I mean, I already said it abstractly here that the classical action generates 3 diagrams because that's what happens when I take 8 bar goes to 0 limit in gamma. But here we see it explicitly. So the classical field, right, is now is obtained from the classical action and is written as a sum of 3 diagrams, of all the 3 diagrams. All right, so that's everything I want to tell you today. Do you have any questions? No? All right. Then please give me exercises.